So let's go and open. Basically, I prefer to use this code just for, making sure that everything will be on one single place in Google. For me, it's easier for me if we just basically use this. Oh, it doesn't show the correct one. You published site. So we will be using this site. So there, if you want to have some Metropolia credits, go and do the enrollment, and actually also to get some feedback for the exercises. Okay. So yeah, if you want 3 credits, then it's 5 exercises, and if you do 2 more, then you get 5 credits from Metropolia. Of course, these 3 credits you probably, well, I'm not sure if you can actually add those into your the study records here, since that's the same thing as what you're doing now. So it's kind of double. On the other hand, you will be working a little bit more. Well, you never know. But anyways, so TX00CQ31. And we are now on signals part. All right. Basically, the exercise 1 has a template here. This is already something what you can do. Download the template and save it to your own Google account. You know how to do it, right? You have the Google account. First, use Chrome. No other browsers than Chrome, since that's the Google browser. Makes life easier. And basically, what you then need to do, you will then log into your Google account on your browser. Then you can start doing things like, make a copy. If you click make a copy, then you can actually move it into your own folder. That's easy it is. It doesn't get easier than that. So, copy of exercise 1, maybe your name also there, just for fun. Okay, now it's safe to edit. It's your copy. By the way, you cannot edit this one. These exercises you can actually do either as an individual exercise or in pairs, or maximum 3 students on each exercise. So you can do group work. That's kind of modern kind of thinking. Well, yeah, the current kind of modern thinking. It's modern. It's not anymore more modern. Since year 2000, at least, starting from then, all the engineering work has been done in teams. So why you shouldn't be doing teamwork already when you are studying? I don't find any reason why you shouldn't do it. So yeah. So with this small group, actually, I would prefer if you do those in pairs, exercises in pairs, or well, alone if you want to. Just remembering that working alone is not anymore engineering. More like a, what is that called? Entrepreneurship. All right, but anyways, on your copy, first things first, mark your names here. First name is enough if you register into this course. All right, and then there are simple questions, 10 of them, each of if each of those are worth of 1 point. And basically what I'm expecting is on this yellow section, in here I expect you to copy paste the commands from MATLAB. Or insert figures. There's an example. I'll just remove that one. So insert a figure. I expect a figure. Write the commands. I expect the commands. Write sound sample. Write the commands and save the sound sample. Okay, I'll just remove that one too. Just for fun. That is supposed to say link to your sample. Oops. There you go. A link. All right. Let me do a little bit of modifications here. Haha. Decibels. Engineering unit. Decibels. Why engineers use decibels? Because nobody else can. And another one. Human senses are logarithmic. If you double the volume of the sound, then basically it feels like a one single step. To get the same power, the feeling, or same feeling of the power change, you will need to double that one. And double, double, double. Okay, that's why we have the decibels. Human senses are actually logarithmic, which is good. Okay, so where did I have my MATLAB? I lost my MATLAB. There we go. Okay, so MATLAB, it's command window driven kind of thingy. You can also start basically writing scripts here. Not a bad idea. Some teachers actually prefer to that you will start writing, editing scripts, and then you can just run those scripts. I'm old school user. I started using MATLAB year 1984 when it was still a kind of beta version in big mainframe computers. Okay, so that's why I'm used to type plenty of things. But anyways, you will be typing a lot of things. So there's not that many things you can click here. It's typing the commands. For example, some commands like variables. Variables you define just by setting the value of them. So basically, this is similar to Python in that sense. You do not need to declare the variable before you start using. You just start using. And this command actually would set variable A to whatever is on the right-hand side. It can be, for example, a value of or calculus, for example. So now, okay, A equals 3. Okay, simple. Then the workspace now has one variable which has a singular value of 3. But that's funny. It says its type is 1 times 1 double. MATLAB is an acronym. It's from Matrix Laboratory. So the fundamental variable type is matrix, n by m matrix of double values. Okay, so you can actually make vectors, for example, like this, either separated by space or comma. Both will do. Okay, that's now vector 1, 2, 3, 4. It's 1 by 4 values vector. Vector can also be 4 by 1, for example. Let's start with the CC. Then the separator is semicolon. 5, 6, 7, 8. All right. If you don't want that one to print out every day, the semicolon at the end is actually the command separator which suppresses the printout. And percent sign is comment. Oops, what happened? Comments. There we go. So no printout, but we still got the this variable here. This is another way of looking at variables. There's a matrix editor. Okay, but that just looks fun. It's just a table. Good. And now we have BB and CC. One is 1 by 4 and another was 4 by 1 vector. We can do some vector multiplications now. So BB times CC. So this is, remember, it's matrix calculator, meaning that if these values are vectors or matrices, it tries to make tries to follow the matrix calculation rules, meaning that, okay, does this make sense? Yes, a row vector times column vector gives you a scalar value. It multiplies each of those element by element, and then basically, so first element of row multiplies the first element of the column, and second to second, and so on, and then the sum of that one. Okay, and the answer is 70. The other way around, CC times BB. That will be matrix, 4 by 4 matrix. I will save it here. Right. So matrix calculations are done really easy here. You just need to know what you are calculating with matrices and vectors, and just start playing around. So yeah, that makes actually MATLAB excellent tool for all sorts of discrete signal processing. Good. That's the start. And then you can actually start making another kind of things like calculating, for example, a determinant. Remember from math? Yeah, and you have been calculating it by hand on paper. Why? It's just determinant of that matrix. And I got 0, of course. Yeah, it was built by multiplying 2 vectors. And then the determinant is always 0. Okay. What else? Then random numbers. Random numbers actually can be generated by rand. If you just leave it like that, it starts saying you, okay, rand one of those forms. Maybe I get some more help. If I click more help, I get this kind of small description which has everything on it. So if you call it just by rand, like that one, it's one single number. Okay, rand of number, then you have n by n matrix of random numbers, and so on. Okay, my favorite way of doing this is actually making random numbers to match the size of a vector. Size of, for example, B, vector B. And these are uniformly distributed random numbers. And if you type exactly the same commands, you get exactly the same numbers. Pseudo-random numbers, meaning that they all start with the same seed number, unless you set the seed number differently. So when you are doing these random numbers and you really want to have different random numbers, you should randomize the random number generator first. Another thing, this is uniformly distributed random numbers. Usually you will be using normally distributed random numbers, and the difference is just a name. Rand is uniform, rand n is normally distributed random numbers, and now we basically have also the negative values there. Okay, to reproduce that one histogram picture, I can always show what the random numbers should or would look like. Rand n, let's make 1 by 10,000 matrix of random numbers. Hist command is the one which actually calculates the histogram, meaning it shows the distribution. And sorry, it came into my other window here. There we go. So more or less the Gaussian shape curve. You can play with this histogram and put there more bins where to calculate those histogram elements, but anyways, it shows the bell curve. Okay, so that's one way of plotting these random numbers. Also, this is the kind of the good way of checking what kind of distribution these random numbers may have. For example, if you have some real data, you first detrend it, take out the signal part basically, and then check which distribution the rest of that one, which should be the noise part. What is the rest of it looking like? Okay, histogram. What else? Then the primary functions. Like delta. For the delta, we basically, let's take a quick look at that. Not there. Quick look at here. Unit impulse. So what we need is an n to calculate the direct delta, and basically there I have from -3 to +5. That's our the region of interest. So region of interest would start. Okay, let's see. Nn equals. Okay, we can make a vector -3, -2, -1, 0, 1, 2. Oops. 1, 2, 3, 4, 5. Okay, that's one way of doing the region of interest. But think of 100 points or 1,000 points. It takes a little bit. You probably also would make a mistake or two there. So you can also auto-generate it from -3 to 5. Okay. So colon operation means from to. From to. And with step size 1. there we go. So NN is still the same. Okay. From -3 to 5. Yes. That's our region of interest. Then we can make the delta. Delta equals. Okay, how does it go? Delta is 1 when n equals to 0 and otherwise 0. Okay, how about if we do it like this? N, okay, let's see, parentheses. N, and then test if this one is 0. This will give me true value on the index that n goes to 0. Okay, yeah. But now it's logical array. Calculations with a logical array is, well, now at 2018 version of MATLAB, it's okay. But they used to be a little bit, say, fizzy. So, and another thing, the true value. What is in C language true? If you test anything, what is true? It's same as non-zero. Anything but 0. 0 is false, but anything else than 0 is actually considered as true. Okay, in that sense, I, as an old school guy, usually use typecasting. Typecasting to double. 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 What is so difficult? Right, double. There. Now it's normal vector of zeros and ones. Good. And we have index from -3 to 5, and then we have that one. Now I would like to have the same plot. If I do plotting, NN and delta, that actually would look ugly. It looks like this. It has the lines. I don't like lines when I'm dealing with the discrete time systems. What I would like to have is a stem plot. There. Okay, so we have 0, 0, 0, and then jumps to 1. Okay, that looks pretty nice, actually. But there's a couple of things that I don't like. Again, I don't like much of the axis here. The data is touching the axis. It's like having a meal where you have, you know, beef and potatoes, and they are touching each other. Okay. Not quite. So basically, I would like to clear this one out a little bit so that you can see the data better. And one way is basically to go here on show plot tools and dot figure. Plot tools. Why didn't it show the plot tools? Oh, it's trying to show me the plot tools. All right. There I can actually do some editing from -3.5 to 5.5, for example. Okay, now I have the this x-axis is so that those points are not on the corner anymore, and then I click on the y-axis. Oh, y-axis limit -0.2 to 1.2. Better. Oh no. Then You probably also would like to add there some information about the what these labels are. So we have index n on x-axis and value arbitrary units. A.u on the vertical axis, and then let's see, title. That was the delta function, actually discrete delta function to be precise. It went there. How to get this title here? Let's see. Font X. Oh, title. There. Discrete delta function. If you want to be fancy, have you heard of latex? Okay, delta. And it recognizes also the latex typesetting comments, most of them. Good. Yeah. Now it's done. But, okay, every time when you make a nice display, you probably would like to also somehow share it with the others. Right, how to get link plot data cursor rotate, save figure. All right, not as MATLAB figure, but JPEG or PNG, portable network graphics. That might be the best way of saving this, since JPEG is always losing some data. GIF is actually good, but I don't think that we have GIF anymore in here. No, because GIF is not free anymore. 1997 was the year that the some company got a patent for a scientific an invention which was made by two other guys, Cooley and Tukey, on a university, but there's a company which filed a patent on GIF. And, you know, it didn't help that there was somebody else made the invention, because company was the first to claim it. Okay. Remember, if you invent something, don't tell anyone. Okay. But anyways, the PNG, portable network graphics file, and it goes somewhere. Okay. Take a look at where it actually goes. So, and basically, you probably also would like to change the name, Delta Fig. There. And now I can go to the file browser somewhere. File Explorer, Documents, MATLAB, Delta. It went to another window. It looks fine, but there we go. Okay, it looks like that one. It looks fine. What I can do for this one actually is something like I think it. Let me try. Just Control C in file browser, then go to your this exercise sheet. Let's see if it works like that. Control V. No, it does not. Okay, in that case, we can actually just insert image, upload from computer, documents, Matlab, Delta Fig. Okay, there we go. That's how you include a figure to Google Docs. Okay, it looks ugly. You should do better. Change the bigger font. So since it's barely, I can barely see it, what it looks like. Let's see. Yeah, well, maybe I can see what it looks like. All right. So that's how you make a picture on these sheets. Stemplot. Let's try then the similar way. We have the another another function, fundamental function, where it is there. Unit step function. So delta function is good if you want to add one single peak somewhere on your data, or want to measure the impulse response of the system. Excellent tool. Unit step you can actually use to start a signal at some certain point. For example, if you are simulating a data transfer and want to start a frequency shift keying signal at some point, you will multiply your signal with unit step. Okay, and same thing, but actually the test is different. So it's 0 if the index is negative and 1 if index is positive or 0. Good. So heavy side, which is also the unit step function. Have you used the term heavy side before? Mathematicians usually like the heavy side naming. All right, so heaviside function. I think there is also a heaviside function on the Matlab, but it's not that hard to make. So u equals the nn is greater than equal to 0, and again I want this one to be a the double vector, okay, and I can stem that one. By the way, the previous command, if you want, for example, a command stem something, so I can go and just write a couple of first letters and then go with the up arrow to find my previous command, which started the same. All right, and there you. Haha. If you're more familiar with typing commands, then you can also x-axis. Set the axis. Oh, wait a minute. Was it axis? Axis or axis? Yeah. Axis and limits. Minus 3.5, 5.5, minus 0.2, 1.2. So instead of going to that cumbersome graphics kind of thingy, then you can always start to comments. The same thing with the labels, X label, X label, and then a string separator. Here is the prime, not the double prime, but prime. And then the text index in like that, and Y label, same thing, value a.u, and then title. Yes, step function new. And again, then copy paste. Another way of actually taking a copy of that picture would be, let's see, can I actually copy figure? I think it goes as a meta file, and then you can move it into your document. Sometimes it gets messy. All right, but that's how you do it. By the way, I'll show you something. Something is missing here. No, home. Where's the Windows? Layout. I want actually the docked command history. So all the time, all of the commands you do are going to command history. And if you then write some code that you want to save, for example, that heavy side, you just paint that part. You can actually run it, or you can create a script. Click on that one. It opens the editor, and when you say save, I can call this one home as example. Whoop. There. Now it's a function that you can call by, for example, one way is just double-clicking that one. And where's the window? Where did it go? Huh? Where's the figure? What? What's happened to my figure? What? Ah, sorry. Not open, but run. Example heavy side. Where did the figure go? Oh, there. Ah, sorry. Oh, yeah, these are the duct kind of things. They are always kind of cumbersome. Okay. So the good part of script is that if you have some changes on your system, for example, if you want to make heavy side with time shift, that would be same as time shift of 2 for the heavy side. Let's rename that one UU2. And same UU2. You just edit that file and then just run it. See where is save. Control S is save. Let's run it again. Run. And that's the step function with time step of right. Mu n minus 1. No, when minus 2, sorry, there. Okay. So it's up to you if you make these scripts or not. All right. Those are the basic fundamentals. Now let's take a closer look at my web page. Where's the web page? There we go. So heavy side, periodic signals. Okay, sampled signals overall. So how to sample signals? Sampling of any signal actually starts from the fact that, well, for example, if you have sinusoid, continuous time sinusoid, x of t is a, which is amplitude times sine 2 pi f times t. That's sample sinusoid with physical frequency of f. When you move that one into the sampled signal x of n, you just replace the t with n time sample time ts. And here the sample time ts is simply 1 over sampling rate. Good. Absolutely nothing fancy about it. So if you have a function, any continuous space function, you just replace the argument of time argument with n times ts. Where that ts comes from? From your system sampling rate. If you have a measuring system or microcontroller system, usually the sampling rates are not that big. Audio, you need 44.1 kilosamples per second at least in order to get a good quality audio. But let's think of a microcontroller. What would be a reasonable sampling rate for a sensor? What is your favorite microcontroller? Or the only one you know? Either or. Which microcontroller you don't hate that much? What is the microcontroller you will be using on this course? Since you are doing also embedded systems processing. Do you already know? Whoa, you have a good processor. You will be able to do audio processing. Some of you will. Sorry. Yeah. Okay. Most of you maybe. All right. So in a high power processor like that one, sampling rate is set by, there are basically two ways of doing it. you set up the A to D converter. If the circuit has an A to D converter, they usually are these peripherals are done so that they can give a the interrupt when the conversion is done at certain rate, since they are designed for this kind of applications. So let's start. Let's try the 44.1 kilosamples per second, although that will be a little bit overkill. Another good number would be 8,000 samples per second. That's good enough for speech. Not good for music, but speech, perfect. Human voice is in hundreds of hertz, and then you add some harmonies to get these hard consonants on it. So 8 kilosamples per second should be enough for most of the voice, the human speech. So sampling rate 8,000 samples per second. Speech. There. And it's still, it doesn't require all the resources from the microcontroller then. Okay, this should be quite doable. And let's think of now your computer, the controller, it samples this sinusoid, for example. Let's make a 800 hertz. No, that's bad. 700 something hertz of signal frequency. So this is the sampling rate of the system. Then you have sinusoid, you are sampling, and that have the signal frequency is 764 hertz. Just for fun. This is the signal frequency example. Okay, now we can do the sampled signal. If we know also the amplitude. Well, with Matlab, we can always play with the amplitude of 1. On your system, do you already know how many bits you have on the on that A to D conversion? It's pretty crappy, actually. I think it can give 16 bits, but it's basically most of the bits are just crap. So 60 bits, that's reasonable. Would you Google the processor and check what is the A to D conversion to the bits, how many bits you get? Then we can actually match this one with your A to D converter. Find anything? It could be also under audio encoder. That's another name for the same thing. And there are, of course, some processors which do not have the A to D conversion, but I know that circuit has, since we use the same circuit also in Metropolia. 12 bits. Okay. 12 crappy bits. All right. To match this one exactly, what you should be having when you are, putting a gain accordingly to the input, and does it say anything about the voltage range in there for the A to D conversion? Voltage range. input range. So it's biased to 2 point something, or was that the either 2.4? It really doesn't make well. Actually, it would be nice since you have this A to D conversion here, and you have unipolar power, right? That has 3.3 volts, I think, the VCC, and then the input range basically means that your analog system has different power. Let me take a quick look at the specifications. Conditions, yes, there are two different range 1 and 2, so either 2.4 to 3.6 or 1.8 to 2.4, and to get the highest sampling rate. Ooh. ADC clock frequency, okay. We can use, for example, the higher one. So 2.4 and 3.6. So this actually has to be biased to 3 volts plus minus 0.6 volts. Right. Okay. Meaning your microphone, this audio signal, must have a gain and also bias circuitry to get it there. One way of doing it, this is the analog electronics. So if you are using this capacitive type microphone, you basically can just use the 3 volt bias. Then this voltage should be around that one. That's one way. Otherwise, you need to do some analog electronics before that. So yeah, so now we know that our amplitude is actually 0.6 volts if it's perfectly matched. It's up to you, of course, as a designer to do the matching. Okay, so 0.6 is amplitude. So our signal A equals 0.6. By the way, the MATLAB, these variables, everything is case sensitive. I had this lowercase AA. If you put the capital AA, it's different variable, the same as in C. All right, so that's 0.6 was the amplitude. And I think this A to D converter itself, it gives then the signal from range is bipolar. It gives okay, the lowest values of that's the 0x00, and here we have 0x, and 12 bits is for nibbles. It's up to 3f, and then we have the minus 0x3ff, which is, well, that you have taken the digital technique, and you know it's not that. It's the choose complement value. All right, so 0.6 is the value, and after A to D conversion, actually, that it looks a little bit different. Was it okay? 7FF, sorry, not 12 bit. 7, not 3, but 7. All right, now it's 3 nibbles. Okay, so our analog signal sampled analog signal would look like x equals A amplitude times sine of 2 times pi times f sig times n, okay, then the t actually is n divided by sampling rate. So remember the Ts equals 1 over Fs. That's our 764 Hertz signal sampled, not converted yet. These are the values. These are the analog values, sampled. Okay. You multiply this one with this heaviside function, which was where u there. Oops. U. Okay, multiplying vector by vector so that you're multiplying element by element is dot times. It's not dot product, but it's actually a element-wise operation. So dot before operator makes it element-wise. There we go. So this is the way to start the signal at certain point. Start it, just multiply it with the this heaviside function. Then that one actually marks those first values to 0. Okay, so that's how you do samples. Longer samples, though, if you want to have, say, 1 second long sample, let's make 1 second long. 1 second long sample with Fs, with sampling rate. Just for fun, I will also calculate the sample time, Ts. I could have also already calculated, but anyways, it's better now than never. Sample time. All right, so if you want to have a longer sections, you don't need to generate the index anymore, since in principle, if you have this one gives you already 1,000 samples there. Okay, you can always just do the sampling like this, XX, not NN. Okay, let me do it. Or we first take the sample time vector. So at the point where the samples we're taking, start from 0 with the time step of Ts to 1. So another way of using column is you have 2 columns. In that case, it's from and to, but in between you put the this delta time. From with time step of Ts to. There we go. And now taking a look at the workspace, TT is 8,001 samples. Well, of course, yeah. 0 comes from the 0, and then the last one matches still the other. So it's 1 more than that 8,000, what we expect. All right, and it looks like this. Oh, sorry. Well, it makes still. So this is not just the sample times, and it's a linear, and it also shows that this type of plotting doesn't make any sense anymore. We have 8,000 samples, and in each individual spot was actually drawn there. Nah, I don't like that one. Even if you do the sampling of the signal now, so instead of that one, we have just the TT. So pre-generated timing. If we plot that one, it does not much makes sense. Whoops, not plot NN, not plot, just plot X. Those are different. It doesn't make much sense of plotting this kind of sound samples, but how about doing something like this? Sound XXFS. Where is my loudspeaker? Playback devices. For some reason, there's supposed to be a sound here, but it didn't sound at all. Anyone else has a Matlab who could actually give in the there's supposed to be a sound, but I cannot hear. Yeah, that's the one. Yes. Yeehaw! That will 700 some hertz sound. You can check it. How many of you are playing guitar or some other instrument? Yes, 440 hertz. A, note A, it's 440 hertz. That's the if you have an ion, it measures that one. Now you can actually run the let's see, x equals 440 hertz. Yeah, that will be 440 hertz. Now you can turn your guitar to that one. Use the tuner though. Guitar tuner. All right, so now we can sample sinusoids. Very interesting. Although, how about making this one more realistic? XX. Let's XX there. Still wondering why it didn't give me anything from here. Sound. Yeah. Got it. It was a setting. Yeah. So this is what a poor sinusoid sounds like. Boring. We can actually make it more interesting by adding some noise. And one way of adding noise, or the only correct way of adding noise, meaning that we need to add a random number for each the sample. So we need a noise for each sample, and that would be size of XX. So this one gives me as many random numbers as I have in my signal. And I can add it there. Okay, on the exercise, you need to figure out the basically amplitude for this noise, how much to add it. I leave that one as a good exercise. It's really teaches you a lot. I will just put the noise amplitude noise amplitude as 0.2, which is same as actually the this is the standard deviation of the noise. Yes. Meaning that NN is actually not that, but N ample times those random numbers, which means that if I choose standard deviation of NN, I should have about 0.2 there. Yeah. But remember, these are the random numbers. Oh, I don't need that one anymore. Not that one either. So if you calculate or measure the standard deviation, it's not exactly that one since we are dealing with random numbers in any case. So with the gazillion random numbers, I will get exactly that one, as a standard deviation, which is the square root of variance. All right. My question is now, what would be the signal to noise ratio of this signal? All right. That was your question. Wow, I've been scribbling a lot. Now the signal to noise ratio is defined. You should know that. Even in the middle of the night, someone comes and your mother comes and kicks you. Hey, what is the signal to noise ratio? What is what is the signal to noise ratio? You will give immediately 10 times the log of. Right, 10 times of 10 base logarithm of power of the signal divided by power of the noise. Right, that's the definition you should remember. And that's something which has been taught to you on the first week when you enter an engineering school. And you should remember that one even when you are, during your last breath. Okay, power signal comes actually handy. Is the power of signal is directly proportional. Let's make it like this. Directly proportional to what? How do you measure signal power? Is the root mean squared thingy. On discrete time systems, it's even easier. This is directly proportional to variance of signal, which is the square of standard deviation. Same thing, power of noise is directly proportional to power of variance of the noise. All right. So now I can actually calculate those variance of the signal, variance of noise, 10 base log and times 10. So signal to noise ratio of this one. So our signal is X and noise is N. And when you combine these, After that, the signal to noise ratio is 10 times log of power was actually variance of signal, which is X, and divided by variance of noise. 6.5 signal to noise ratio, which is not great. So there's plenty of noise, which is good. All right, and then the combined, so noisy signal is simply, what did I say? Adding noise. Add a random number for each sample. Noisy signal is xxnn equals xx plus nn. There we go. That's the noisy signal, and it sounds like this one. So it has a shh on it. That was the noisy part. All right. Only a couple of things to do for this exercise. Now, one is in my exercise, I'm asking you to make that sound sample available for anyone. So practically what it means, it needs to be just saved in some good format. For that one, we need audio write, the function. Let me find it. Doc audio write. Wow, why it has so small fonts? Preferences. What? Well, you will see it better in your display. But anyways, audio write actually writes an audio file. WAV files are quite nice. Or it's easy to find the WAV file writer, or actually MP4. It can also save these as MP4s. So basically what you just need to do is to call audio write with file name, data, and sampler rate. Okay, there. So how to save that audio recording would be audio write, file name, that's a string, sound1 dot wave, then the sample rate, and data first, xxnn, and then sample rate. There we go. Data clip when writing file. Okay, in principle, you should normalize all of these sounds between -1 and 1. When we added some noise, since amplitude was for the signal was 0.6, when we added some noise, some of those values actually went above 1 or below -1.1. So in that sense, actually, before saving and to make sure that you get everything what you really want, there is to okay, we will normalize the signal. Easiest way of doing it is xxnn equals xxnn divided by maximum of absolute value of the signal. That should do the trick. So now if it was negative, actually goes the that should be fine. And doing the audio write again. There. No warnings. There we go. Now we have the sound1.wave file. Woohoo! I got it as a wave file on, let's see, in here. Okay. You can actually, for some reason, you can actually do a link to your C, your own computer, and no one is complaining about it. So in here, when you make a link to your sample, what you should do first, before that one, you should upload this WAV file to your favorite audio repository and get a link for that one. Okay. One good audio repository would be just Google Drive. All right, so let me go to Google Drive. My Google Drive. And we are working on, okay, I'll just put it here. Google Drive. Somewhere in there, it's up to you where you put it, but anyways, I like some sort of okay, I'll just make a new folder here. Full bar. Full bar. Okay. Sound. Copy it there. Not done yet. You need to share it. Okay. Let's see, where is it? There. Okay. Go on. More. Anyone with the link can view it. Okay, that's very important. If you do not do it, then I cannot check the link. Same thing goes with the, okay, there. That's the link. Same actually goes with this one. When you have done the exercise, you share it. So that anyone with the link can actually anyone can find and view. Yep. Now if I copy that one, now it's actually, I can submit the link. Okay, so basically remember those sharing things before submitting. So practically, so we have covered now. See, where did we start from? Setting up variable, setting up vectors to kind of multiplying vectors, doing some random numbers, histograms, indexing, meaning sampling index, using that index to generate delta or the heavy side, setting the axis of systems, then sampled signals, sinusoid. So just remember you do not mix the sample rate and the signal rate frequency. Then added some noise, meaning random numbers. We calculated the signal to noise ratio. On the ninth exercise today of the first part of the exercises, there is signal to noise ratio is given. You need to go back and calculate the standard deviation of the signal. So you need to calculate actually this noise amplitude. So you don't know that one, but you know signal to noise ratio, signal you generate yourself. You can measure then this signal variance, and from this formula you can then calculate what is the noise variance, and then use the standard deviation, which is just this part, as a noise amplitude. And use that one to multiply the random numbers. Then you got it all correct. Okay. Then how to sound those samples, and yeah. All right. So I think I have covered everything for the first exercise. How far is your MATLAB installation? Yes. Okay, so for the rest of today, we'll wait for MATLAB to install, and then basically also the have lunch maybe. And I will be here answering questions until 4 o'clock. Good. And otherwise, you can start working together on this exercise. And I recommend also you to, well, it's not that much more work to get the credits also from Metropolia, so go ahead and register on this website to the course. It doesn't hurt. And by the way, I will actually on each day I will copy this command history and post it actually on the website. All right. That's 8. And I usually don't do much of the editing, but there.